In this video, we are going to continue our discussion regarding Wgans, and we will learn about that gradient penalty. So, what were the problems with VAT clipping? First of all, by clipping the VATs, we were limiting the model's ability to learn, so its capacity is underused. The second problem was the gradient exploding and vanishing. So if the range of the gradient clipping is big, then we might face the gradient exploding problem, and if the range is small, then we might face the vanishing gradient problem. And this third issue with gradient clipping was that it was pushing the VATs to the two limits. So in 2017, another paper with the name Improved Training of Wasserstein GANs were published, and they actually showed that phenomena. Here, as you can see in these two images, on the top one they have applied the VAT clipping, and in the VAT clipping our VATs has been pushed to these two limits. So most of the VATs are negative 0.01 and positive 0.01, and there are very little VATs which are between these two ranges. So VATs clipping method pushes the VATs or most of the VATs to the limits of the range. But using the gradient penalty method, we can see a fairly smooth graph. So that's why this paper, Improved Training of Wasserstein GAN, proposed this gradient penalty method in order to enforce that one Lipschitz constant. Now let's talk about gradient clipping. Gradient clipping penalizes the norm of the critic's gradient, which is this. It's like L2 norm of the critic's gradient with respect to each input independently. So it's really important. We are not going to apply this gradient penalty batch wise, but instead we are going to calculate it for each independent example. So what this gradient penalty does, it keeps the norm of the gradient at most 1 everywhere. So that's why our output isn't going to explode, it will be smooth. And now this is the mathematical equation which was proposed in the paper. So instead of using now just the original critic loss, we are going to add this gradient penalty term to the total loss as well. So this term represents the loss of the generated images. This term represents the loss of the real images. So it's basically the critic score for each image. And then this term represents the gradient penalty. So let's expand this term. First of all, this was the theorem proposed in the original paper. In order to calculate this term, we need to follow these steps, these three steps. Firstly, let's expand the notations a bit so that we could understand this theorem easily. The x tilde represents the generated image. So as you can see, the first x tilde means it's the generated image, and then this x hat represents the resultant image of pointwise interpolation between real and generated image. So this x hat is the pointwise interpolation of the generated image, which is this x tilde, and the original image, which is this x, and this epsilon is the random noise drawn from the normal distribution. And this term is the gradient of the interpolated image's score, which is basically the critic's output with respect to the interpolated image. So this del means the gradient, and this x hat means we are going to find the gradient with respect to this variable, which is our interpolated image, and then dw, and this x hat means the score of the critic for this interpolated image. Now let's see the coding part of this. First of all, in order to get this epsilon, we are going to use the normal distribution, and we will randomly sample from this normal distribution. In order to generate this interpolated image, what we will do is to multiply this epsilon with the real images, and then 1 minus epsilon with the fake image. Once we have the epsilon interpolated image, all we need to do is to calculate the gradient penalty loss. For this purpose, we are going to use the tf.gradient tab because we need gradients. Only then we will be able to calculate the gradient penalty loss. and I'll call this gradient tab as penalty gradient tab. And we are going to watch for this interpolated images because we are going to find the gradient with respect to this interpolated images. Then we are going to pass our interpolated image to critic, which will return us the interpolated images score, and using this interpolated images score we are going to find the gradient. So our interpolated images gradient will be the gradients of interpolated images score with respect to this interpolated image. So this is like y, my function, and this is the x with respect to which I want to find the gradients. So once I have this interpolated images gradient, now I need to put it in the formula to get my gradient penalty loss. For this purpose, first of all, I need to calculate this term, which is the norm or L2 norm of this interpolated images gradients. And in order to calculate this L2 norm, I hope you are familiar with the L2 norm formula. If not, just go to the Google and search for the formula, and it's quite simple. It's just like the square root of the square sum of all the numbers. So for this purpose, first of all, I'm going to square my gradients or these interpolated images gradients. I just named these interpolated images gradients to grades in order to save some space. So once I have the squares, then I need to find the reduced sum because I need to sum all the numbers, but I'm going to sum each sample separately. I'm not going to sum whole batch. 0 axis represents my batch dimension. I'm skipping that batch dimension, and once I have this term, all I need to do is to square root this GP loss in order to get a new GP loss. And now I have this term right here, as you can see in this formula, this L2 norm of the interpolated images gradients. Now I just need to subtract 1 from it, then square it, find the reduced mean, and multiply it with lambda. So in the original paper they proposed the value for lambda as 10, and it works fine across different data sets and different architectures. So all I need to do is to subtract 1 from this GP loss, then square it, then find the reduced mean, because now I am going to use this as a loss, and then all I need to do is to multiply this lambda term with this GP loss. So this is how we are going to calculate this gradient penalty term. Once I have this gradient penalty term, all I need to do is to put it in my previous formula, which is this. So now I have this term, just put it right here, calculate the score for the real image, calculate the score for the fake image, and then sum them all, and you will get your total loss. And this is what we are going to do in the next video. So we will combine all the pieces of this Wgan architecture and we'll create our model in TensorFlow. So I'll see you there. Bye bye.